Okay. So we've been talking about probability for a while now. And probability, of course, is useful in a lot of different ways. We can use it to not for 100% determine what the future is going to hold, but we can use it to get a prediction. Okay? So today I want to relate probability to something that we've been talking about on and off throughout the semester, and that is a normal distribution. So a normal distribution looks like this. Okay, it's a nice curve. I could have done better drawing it, but this curve represents our data. And so if we have continuous data, as the curve rises, we are seeing data points that have higher and higher frequency. Of course, that means that they are occurring more and more often. And we can say that then the highest point, which is right here, would be the data point that occurs the most often, which, what do we call the data point that occurs the most often? Is it the mean, median, mode, or range? The mode, yeah. So where our data is most frequent, that is our mode. Now, we have seen in previous chapters that if we have a normal distribution, so this is exactly evenly dispersed, so this side looks exactly like this side, even though I haven't drawn it very well. that this doesn't just represent the mode, that this also will represent the median and the mean. So all three of those end up landing right there in the middle. And of course, that is if we have a perfectly normally distributed set of data. If it gets skewed to one side or the other, well, then it's not as normally distributed anymore. Okay? So, some things that we can determine from this is, first of all, if this is also where the median is, that's the middle number. That's right smack dab in the middle of all of our data. So half of our data would be below that point. Or of course we could say that is 50% of our data. And on the other side, of course, that is the other 50% of our data. Make sense so far? Okay. So again, if this is perfectly normally distributed, both sides are symmetrical and they represent 50% of our data on each side. So we could say that if we just choose a data point at random, so just reach into here, pick up one of our data points and look at it, there's a 50-50 chance that it is below the mean or above the mean. Of course, that means that the probability is 1/2 or 50-50. Now we've also learned that we can measure and break up these distributions using what is called a standard deviation. So standard deviation, just as a refresher, is sigma equals the square root of the sum of all x values minus the mean squared divided by n, the number of data points we have. And so what this does for us is it tells us how much the data varies and gives us a way that we can break up the data in even measurements. Okay? So each of these new little slices that I've made here would represent a single standard deviation. Now, standard deviation is a measurement of distance from the mean, distance from the average. So how far does this point vary from the average? How different is it from the average? Well, it's 2 standard deviations, 2 standard deviations. Okay, so again, standard deviation tells us how this thing is varied. What are the differences between our points of data? And we can use this to start finding some new things. So let me give you an example. Let's say that we're at a light bulb company. And of course this factory is producing light bulbs. And after testing these light bulbs, we have found that on average a light bulb lasts 1,000 hours. Okay, again, average, that's the mean. So that is our mu. So again, on average, light bulb lasts 1,000 hours. However, not every single light bulb lasts 1,000 hours, of course. Some of them last a little bit less or more. And so by calculating a standard deviation for all of these light bulbs, we find that there is a standard deviation, sigma, of 100 hours. So if we think back many chapters ago, we can then say that within one standard deviation of our mean is most of our data. So we can say that, let's see, that would be between 900 and 1,100. So most light bulbs are going to be somewhere between 900 hours and 1,100 hours. But let's take it a step further. Maybe we want to know what is the probability of a light bulb, just a single light bulb. We chose it at random off the assembly line. What is the probability that that light bulb would be a light bulb that lasts at least 1,200 hours? Again, what's the probability that it will last at least that long? So, less than or equal to 1,200. Okay, for this we actually need something new. We need a new calculation called a z-score. So what a z-score does is it looks at a particular point in our data, in this case 1,200. And that z-score calculates the area behind that data point. So in this case, 1,200, that's going to be somewhere around here. I'll make it a big, thick line. Okay. So if 1,200 is right around here, what we want to know is how much of our data is behind it. So what is the area of this shape behind it? And that will give us the probability. Make sense so far? Okay. So how do we calculate a z-score? Well, again, it's a new formula for us, but thankfully it's not one of these monsters. It is only z equals x minus mu, the mean, over sigma, standard deviation. Pretty simple. Now, of course, if you're given raw data, you're going to have to calculate that standard deviation on your own, but luckily for us, it's already given to us. We already know that the standard deviation is 100 hours. So at this point, what we need to do is we just need to plug these numbers into our formula and see what we get. So let's go ahead and do that. Z equals, again, the x that we're looking at here, the data point that we're looking at is 1,200. And from that, we're going to subtract the mean. We're going to see how far this thing is from the mean. So our mean is 1,000. And then we're going to divide this distance by the standard deviation, or how much it varies. Really, I should say the distance of variation. All right, so let's go ahead and calculate. Of course, first we need to figure out what the top part is. So 1,200 minus 1,000, or 1,200 minus 1,000, what's left over? $200. Okay. Okay, and it's still over 100. So now we have 200 divided by 100, and that gives us z equals 2. Now we aren't quite to our probability yet. In fact, there's another calculation that you do after this, once you get your z-score, to get your probability. However, no one in the real world does that. No one in the real world calculates off of a z-score because it's already made up for us. Okay? So if you go online or look in your statistics textbook or what have you, you'll find a chart that looks like this. This is what is called a z-table. And what it does is it takes a z-score and then relates it to a probability. All of these numbers here in the table are probabilities. Okay? Now we actually have two different z-tables. They do the exact same thing. Again, they find the area behind a particular data point. So both of these are doing the same thing. However, this z-table is for z-scores, the thing that we just found, that are negative. Well, is ours negative? No, it's positive. So we need the table that gives us positive z-scores. Again, two tables, they do the exact same thing. One is just for negative z values. This one is for positive z values. So let's look at this one. Again, the z-score that we got was positive 2. So we need to look up positive 2. And this is how it happens. You look at the first two digits. So in our case, that is 2. We look for 2. There it is. Okay, so it's 2 point what? What is this number? 2.0. There's nothing after it, right? So it's 2.0. So we need to find 0.0. Then we line them up, and they intersect right here. This is our probability. So this number right here is 0.97725. Let's write that down. Probability equals 0.97725. One of these tables? Absolutely, I will. In fact, on Friday, I'm going to try to print a copy off for everybody so they can just have one. It'd be torture on y'all to not give you one of these. Okay, so that is our probability. If we select one of these light bulbs at random from the assembly line, there is a 0.97725 chance that it's going to be less than or equal to, or at least 1,200 hours of life. Now, of course, we can make this into a percent, so it makes a little bit more sense. Just move that decimal twice to the right. And so as a percent chance, this is 97.725%. So 97 or almost 98% of the time that we choose a light bulb at random from this assembly line, it's going to have a life of at least 1,200 hours. Is it guaranteed? No. We might choose one that is more than 1,200 hours. However, the probability tells us that if we choose it at random, we're likely to find one that is at least 1,200 hours. I've been saying at least, I'm sorry, no greater than 1,200 hours. Been saying it backwards this whole time. That's my dyslexia. I'm sorry about that. Okay, so any questions? So again, what we just calculated is the chance that if we select a light bulb at random, it's going to fall somewhere in this shaded area. So it could be 1 hour. It could be 50 hours. It could be 100 hours. It could be all the way up to 1,200 hours. It could be over that, but the probability tells us that it's probably going to be somewhere back here, less than 1,200 hours or equal to it. Does this make sense? Okay, good. So let's try another one. Let me just find, there it is. Okay, So let's try this one. Again, same idea. We have a normal distribution. Our mean is still going to be in the middle. It will always be in the middle if it is a normal distribution. Same for the mode and the median. And what data are we looking at here? Heights. Let's say we go out on the university and just take a sample of people's heights and then extrapolate that to a population. What we would probably see is that most people are somewhere right around just above 5 feet. Okay, so that's going to be our mean, our average. So let's say that our mean is 5.7 feet, just above 5 feet. Well, does that mean that everybody is right around that mean? No. Most people will be. Again, most people are going to fall somewhere within 1 standard deviation. So 1 standard deviation below or 1 standard deviation above. This is where most of our data is going to be. This is where most people are going to be. Some people are going to be a bit taller than that though. Like me, I'm 6'7". I'm pretty tall. Those other people are going to be much lower than that. Okay? But most people are going to fall within this range. Now, let's say that we know some data. Again, we know that the mean, mu, is 5.7. And let's say that this doesn't vary all that much. Let's say that our standard deviation is only about 0.3 feet. Okay? Now, let's see. Let's find the probability, or the percent of people that fall below or equal to 6 feet. So all the people that are 4 feet, 5 feet, 6 feet, and everything in between. All the different things that could be below 6 feet or equal to it. So basically we're just singling out the people that are not above 6 feet. Does that make sense? Okay. So, do you expect that number to be high or low? Do you think that there's going to be a lot of people who are 6 feet or below? Or do you think there's going to be a lot of people that are above 6 feet? Well, let's find out. Let's find our z-score and find our probability. So again, z-score is x minus the mean over the standard deviation. So we'll plug our numbers in here. The height that we're trying to find below is 6. So people 6 feet or below, minus the mean, which most people apparently are around 5.7 feet. And then the standard deviation is 0.3. Okay. So, I'll get my calculator real quick. 6 minus 5.7 is 0.3. Ooh. Over our standard deviation is also 0.3. Well, what does that mean we get? What's 0.3 divided by 0.3? 1. So our z-score comes out to be 1. All right, is this a positive or negative z-score? Positive, yeah. It's a positive 1, so we need our positive z-table. Okay, so we need to find 1. Just look down here. There's 1. And it's 1 point what? Well, did anything come after that 1? So it's 1.0. So find 1.0 is right there. And then they match up here. That is 0.84134. And there's our probability. Of course, this means that, let's see, 84.134% of people are 6 feet or below. Which makes sense. Yeah, most people are going to be 6 feet or below. There's not a whole lot of people out there that are really, really tall. Does that make sense? Okay. Any questions? None? All right. Let's try a new one. And I don't have an example to go behind this one. This is just random numbers that I came up with this morning. Again, we have a normal distribution. Our mean, median, and mode are in the middle. And we're going to say that the mean is 79. With a standard deviation of 13. Okay? So what we want to find now is the percent of data that falls below or equal to 54. Okay, well again, let's think about it. In our previous examples, our x, the number that we're looking at, was above our mean, which meant that we had really high probabilities. In fact, we had positive z-scores. This one, 54, is below our mean. And so when we plug things into our z formula, let's see, 54 minus 79 over 13. 54 minus 79, is that going to come out to be positive or negative? Negative. 54 minus 79 is going to be negative. In fact, it's going to be negative 25. Which means that this whole thing is going to be negative. I'm going to have a negative z-score. Let's see what it comes out to be. Negative 25 divided by 13 is a z-score of negative 1.923. And the decimals keep going on and on, but I don't need all of them. Okay, so again, we have a negative z-score here. That means that we need our negative z-table. All right. So, negative 1.9, we look through here, find negative 1.9. There it is. And then we look for the next digit, which is 2. We have 0, 1, 2's right there. And so if we follow this down and over, they intersect right here at 0.02743. And as a percent, of course, we move that decimal twice to the right. So we can say about 2.7% of our data is at or below 54% of 54 on our table. Which makes sense. Since we're below our mean, we're dealing with a lower or smaller area. Any questions? Okay. So like I said, these two z tables calculate the exact same thing. If you have an x value, it'll calculate the area behind that x value. But what if we don't want that? What if we don't want to know less than that x value, but we want to know greater than that x value? So above, not below. Well, these z tables don't tell us that. They only tell us below. Now, I'll preface this by saying there are z tables that you can find out there that do calculate above, but they're not necessary. I would not bother at all with them, and here's why. Again, let's think about our normal distribution. Like I said in the beginning of class, this middle point here is our median. It splits our data perfectly in two. 50% is on this side, 50% is on this side. Well, what's 50 plus 50? 100%. So the entire thing all together represents 100%, right? Okay. Well, what is 100% as a probability? So what we've been doing is going from probability to percent. We need to go the opposite direction. We need to go from percent to probability. So we move that decimal twice, right? Well, 100%, move that decimal 2 times, we get 1. So we can say that, yeah, this is 100%, but as a probability, the whole thing all together represents 1. Okay. So let's say that we don't want to know less than or equal to 54. We want to know x is greater than or equal to 54. So what we found before was this area. But we don't want to know that area. We want to know this side. We want to know greater than. Well, it's pretty easy. If we don't want to know this part, but we want to know this part, we just break off this part, subtract it, literally subtract it. So if we know this area right here, we know that it is 0.02743. If we take that away from the entire thing, it will give us the other side. It'll give us the stuff above that. Like I said, we literally subtract it. To find this side, we do 1 minus this. Take this off and we'll just be left with this, right? So 0.02743, take that away from 1. Let's see what we get. 1 minus 0.02743 is 0.97257. So, we can say, if we move this decimal, that about 2.7% of our data is here in the unshaded region. But 97.3% about is here in the shaded region. Does that make sense? Good. So you don't need another type of table to tell you the stuff above this point. All you need is to find this and then subtract it from 1, because it'll give you the other side. So really all you need are 2 tables, not 4 of them. Any questions? Okay. So, Friday. We've seen how to calculate above and below. Friday, what we're going to do is we're going to see how to calculate in between. All right? But until then, I hope you have a great day. That'll be it for today.